Logarithmic functions and exponential functions are inverses of each other, and that is to say, if we have an exponential function f of x equals b to the x with a base b, then the inverse of f is going to be log base b of x. They have the same base, you see. To see what's meant by this, let's consider y equals 2 to the x. If x is -1, that -1 is going in the exponent with a base of 2, and so the answer is 1/2. If x is 0, 2 to the x is going to be 1. And if x is 3, then we get 2 cubed, which is 8. For the inverse, which switches x's and y's, if the input value is 1/2, then the log base 2 of 1/2 is going to be -1. I didn't get that by thinking about it over here. I got that by reversing x and y from the previous table that we looked at. Likewise, if the input is 1 for the log base 2 of x, the output will be 0. So the log of 1 is 0. And finally, if the input is 8, then the output is 3. And this last statement is the one I kind of want to focus on here. We've got that the log base 2 of 8 is equal to 3. The reason for that is that with a base of 2, putting an exponent of 3 on the base gives me the result of 8. Since 3 is playing the role of an exponent, we can see that a logarithm is an exponent. That's all it is. It is the inverse of an exponential in terms of functions, but the thing that we're calling a log is just another name for an exponent. Now with that in mind, and kind of out of the way, we're going to consider the inverse relationship a little bit further. For the exponential function f of x equals b to the x, we know that the domain is all real numbers. The range goes from 0 to infinity, and we have a horizontal asymptote of y equals 0. Since the inverse of a function effectively switches x's and y's, it switches domains and ranges. And so for the inverse function, the log base b of x, we get that the domain is 0 to infinity, which had been the range of the original function. The range of the logarithmic function is all real numbers, which was the domain. Switching x and y also means that our logarithmic function has a vertical asymptote with an equation of x equals 0. We can translate this information to graphs. We aren't going to spend much time graphing logarithmic functions. That's more for intermediate algebra, pre-calculus, but what we have here is a graph of y equals b to the x for b greater than 1, and we see that's a function of exponential growth, intersects the y-axis at 0, 1. The inverse function is a reflection about the line y equals x, and the graph of y equals log base b of x is that reflection and goes through the point 1, 0. Looking at this graph, we're going to look at another one in a minute, but looking at this graph is useful for determining limits. We can see here that the limit as x approaches infinity of the log base b of x is equal to infinity, and we can see here that the limit as x approaches 0 of the log base b of x is negative infinity. Now I don't know if you notice, but I just made a subtle mistake. It's that when we approach 0 along the curve for the logarithmic function, we can only approach 0 from the right. Remember, the domain of the logarithm only includes positive numbers. When I wrote the limit as x approaches 0, I implied that x was approaching 0 from the left and the right, but it's only approaching 0 from the right. And so it is required to say the limit as x approaches 0 with a little positive exponent looking thing, so 0 from the right, of log base b of x is equal to negative infinity. Now I said we were going to look at another graph. The other one is for a base b that is positive but less than 1. If our base is less than 1, then our graph of y equals b to the x shows us exponential decay. The reflection about y equals x will give us the graph of the logarithmic function. Y equals b to the x goes through the point 0, 1 again, and so its inverse goes through the point 1, 0. We can again see from the graph that we have a couple of limits. One of them is that the limit as x approaches 0 from the positive side of the log base b of x is equal to infinity for a base less than 1. And the limit as x approaches infinity of the log base b of x is equal to negative infinity, again if the base is less than 1. And I neglected to label my graphs here, so this one is y equals the log base b of x, and the one with exponential decay I did label. All right, so we're cool there. So these, like with exponential functions, if I have limits that I need to compute with logarithmic functions, I'm generally probably going to be picturing graphs, if not drawing them. Revisiting this idea here that log base 2 of 8 is equal to 3 because 2 cubed is equal to 8 gives us a couple of different forms that we can use to write equations. So we note that the equation log base b of x equals y, which is an exponential form, is true if and only if b to the y is equal to x. That equation is an exponential form. And again, what we see is the base is b, the exponent is y, so a log is an exponent, and then x is the result that occurs when we take b to the exponent. And at this stage, this should be review. Maybe I'm clearing some things up, and if you know everything that I'm saying already, cool, we're moving on.